Okay, so thank you very much. So it's like for the speaker, of course, a great honor to speak here in the memory of Jean-Pierre. So I also have many memories with him, and as it's kind of the hyperbolicity day, of course we have to say that, especially in France, the development of this field of research is probably, we owe a lot to him because of his enthusiasm. And also, I remember that being a PhD student, probably this was my first seminar in Grenoble when he invited me, and he was so enthusiastic that we were very happy to work in this field. And I have, since my PhD, I've had many discussions with him until the last period of his life, and he was still so enthusiastic. So today, in fact, I will also speak of things very much related to the work of Jean-Pierre. And I want to somehow speak about two recent works. So one in collaboration with Bartsch and Erwan Rousseau, and the other one with Stefan Kebekus. So they kind of have the same setting. So I will start by recalling these two notions. So specialness and hyperbolicity are really two opposite notions. So I will start with recalling the definition that was already recalled this morning by Gergely. So X complex variety is said to be Brody hyperbolic. So this will be the notion of hyperbolicity I will consider. If so there is no entire curve, so there is no non-constant holomorphic map in X. So there is no entire curve in X. And special, so here I will take the analytic version. So of course this everything concerning specialness is due to Campana, so we'll take his definition. So here we say that X is Brody special if it is non-hyperbolic in a strong sense. That is, not only there is an entire curve, but there is a Zariski dense one in X. So these are the notion I'm interested in. And as Simone recalled us, one of the main goals, leading ideas, is can we characterize these analytic properties by purely algebro-geometric properties? So I recall, so the main question is, can we find geometric characterization, algebro-geometric characterization of these two properties? So the first one was recalled by Simone, but this is Green-Griffiths-Lang conjecture. So hyperbolic, so if you take X projective, so first of all, we have a weak hyperbolicity property that if X is general type, this should correspond to a weak version of hyperbolicity in the sense that all entire curves have to lie in a proper algebraic subset. So here I will not recall every time it's an entire curve, so holomorphic non-constant, such that, and this immediately implies as a conjecture corollary that the characterization that Simone explained us just by induction, that from this conjecture you immediately get that hyperbolicity should correspond to the fact that X and all its subvarieties are of general type. So this is the classical side of the story. And the other one, which I will be more interested today, is this one, which is less classical. In fact, it took some time to arrive to kind of good conjectures. So how can we characterize Brody specialness? Of course, both problems are related. You see that if X is Brody special, certainly it shouldn't be of general type, right, by length. But you can somehow elaborate on this. So if X is Brody special, so X should not be of general type. But more generally, you should not have the following possibility, that you should not have a finite étale cover of X which would dominate a variety, a positive dimensional variety of general type, right? Because if you have an entire curve here, the risk is that it would lift by étale cover, and you could project it down to something of general type, right? So this is now usually called this property. We say that X is weakly special, because there will be later a strong special property. And in fact, this kind of property were in the literature, I think, first considered by people from arithmetic, related to this kind of model problem. So they were, I will talk about this in a moment, but if you look at the analog in arithmetic, you are looking at variety with dense set of rational points. And they were looking for a geometric characterization. And this was a conjecture by Abramovich and Kolyotelen. That maybe this was the good geometric characterization of the equivalent of specialness for arithmetic problems. So you could ask the same through a Lang dictionary. Maybe this is the good characterization.
In this conjecture, you assume X to be projective.
Yeah. Yeah. X is
always projective.
Yeah. You can, in fact, I will do a more general setting after. You can do that for pairs. But yeah, we'll go that in a moment. So the question is, somehow coming out, is it the good characterization? And the answer is no. This is not the good characterization. So by result of Frédéric Campana and Mihai, so they exactly disprove this. So they prove that there exists some projective variety. I will explain the example in a moment. So X weakly special, but not broadly special. So they show that in these X, all entire curves are degenerate, algebraically degenerate. And the examples are really explicit. This comes from example by Bogomolov and Chinkel. So those X are constructed by Bogomolov and Chinkel in the following way. So we'll briefly describe them. So they are dimension free, simply connected. So this helps to check the property because you do not have non-trivial étal cover. Weakly special, but how will come the fact that so not broadly special will come from a geometric property of this example that they come with a fibration. There exists a fibration onto a surface so in this case, it's elliptic surface. And what is particular with this fibration is that you have a smooth curve inside B such that these fibrations have multiple fibers above this curve. Fibers over T of some multiplicity n, and you get some positivity coming from this. Because now, in fact, what you should really think is not that a fibration has a base which is B, but has a base which is a pair encoded by B and the divisor encoding multiple fibers. So the key fact is that, in fact, the pair even though B is not of general type, the pair becomes of general type. So delta phi is just the divisor encoding multiple fibers. And this is, so I will come back to the ideas of the proof, but this is exactly what Campana's definition tells you, that this should not be considered as special. And he conjectures that, in fact, this kind of phenomenon is exactly what should characterize broadly special varieties. So there is a... can we do that with that? No, it's not good. OK. I don't want to break the system. Great. So here comes the definition of Campana. X special exactly if you do not have this phenomenon, so there is no fibration with orbifold base of general type. And there is also a very nice characterization of this looking at rank 1 coherent subsheaf of differential on X, which is really like in the spirit of Lang. So Lang says you should look at the canonical bundle. Here Campana says if you look at this, you should look at all exterior powers of the cotangent bundle. So the definition is for any rank 1 coherent subsheaf in omega xp for any p, then the Kodaira dimension, so by a theorem of Bogomolov, you know that in this situation, the Kodaira dimension will be at most p, and here you ask that it's strictly less than the maximal possibility. And you kind of easily see the link between these two. So you see that from such a fibration, how do you get such a L? You just pull back orbifold forms on the base by F, and you get your sheaf inside. And so now you have these conjectures of Campana, which says, okay, X Brody special should correspond to special in this sense. And you have also, as I say, motivation originally come from arithmetic, and I will speak. As you imagine with Ariane, we have more arithmetic flavor since it comes from arithmetic geometry. So I will mention this because this has attracted a lot of attention. So this is kind of a generalization of Mordell conjecture that Robert told us yesterday. So if X is defined over a number field, K, so we say that it's potentially dense. So what does it mean? It means that rational points are dense up to a finite extension of the base field. So there exists finite extension such that rational points are dense. And you have the same conjecture that this should occur only if X is special. And as I say, the dimension 1 case is essentially Falting's statement. Because, of course, in dimension 1, you exactly know what are the special and non-special according to the genus, right? Yeah. No. I take any number field which is already a finite extension of Q. So this statement is you can formulate for any number field, right? So X is not necessarily defined over Q at the beginning. It can be defined over any number field. So now, more importantly, comes the strategy of proof. For this kind of conjecture you would like, so of statement like, I will explain it for Brody special implies special. But of course, you can replace this for any property. This will be kind of the same strategy always. And strategy is kind of very simple. So you will suppose it's not special, and you want to prove that it's not really special. Suppose X not special. So by definition, as in the example of Bogomolov-Chinkel, it comes with a fibration onto a pair of general type. Right? And now you want to study, you want to prove that intercurves in X are not Zariski-dense. What do? You send everything here. So now you are reduced to study intercurve in Y. But these are not arbitrary intercurve, right? Because these encode multiple fibers. So it tells you that downstairs on Y, so you have the curve, the support of D. It means that when you send down your intercurve, it will have some tangency property with this, right? So it will have to be tangent at least to order M. So this is what is called orbifold intercurve. So you see, you arrive kind of in the same philosophy as in birational geometry, but for other reason, is that you want to extend all classical results to pairs. So here, yeah.
C composed with this one, it must be orbifold if it's exactly some exception.
No, yeah, you have some agreeing some. Let's just focus, for example, in the case of Campana pawn, right? There it's just very simple. So you can have technical difficulty. I'm just explaining the strategy, right? So the key point is, in general, that to prove this kind of result, where you have a priori no boundary on X, you are reduced to prove some statement, like Green-Griffiths length statement for pairs. Okay, so obtain some Green-Griffiths length statement for pairs. So now I will mention what kind of classical statement I'm interested in. So these are what was successful for varieties without boundary. So first, and then the outcome is that there are some surprises. So things do not work like we would like. So first kind of surprising statement is you have for varieties, you have the nice statement of Jean-Pierre, which says that if X variety of general type, then, as I will not recall everything, Gergely did it this morning, you have this jet differential strategy to attack Green-Griffiths length conjecture, and Jean-Pierre proved a very nice statement that if X is of general type, you can always find a jet differential. So there exists possibly big K, big M, such that you can indeed find even twisted by an ample line bundle. So you can start the strategy you would like. So this is the first statement. So, okay. So we were at first thinking, well, it will. So this also works in the log setting. If you take just reduced divisor, right? But if you take like orbifold divisor, this statement turns out to be wrong for orbifold pairs. And for very simple pairs. Just take, for example, P2, a smooth curve, and multiplicity 1/2. And D, degree of C, as large as you want. So, in fact, this comes out from the description of what are the analog of this object, which is kind of, you don't have too many choice. You look at differential operators acting on orbifold curves, right? And when you get the analog of the filtration, in fact, you see that starting from a pair, the different terms in the filtration will make appear differential of other pairs, where you will have, unfortunately, to change the boundary. Because when you differentiate curve, it also interacts with the vanishing, of course, tangency. And this is where you change. So you see that the order comes into the picture. And at some point, you even get rid of the boundary. And it's very easy to see that here, for this, you simply have never, even without twisting, you never have global section. So this was kind of a surprise, but it's the first occurrence, we'll see others, where usual strategy fail for pairs. But it can work. And this was done by Campana and Pound. So other classical statement is theorem of Bogomolov-McQuillan, where you will stay working with one order jet differential. And so the classical statement is that if S is a surface of general type with C1 square S strictly bigger than C2, then you have two very nice statements. First of all, one of algebraic nature. Yes?
Maybe it's less interesting case, but so when you say that the Mailly's theorem doesn't work for these pairs,
I mean, there are counterexamples.
yeah, of course.
Yeah.
So the pair you are looking at is the manifold itself is totally not of general type, and then it becomes of general type.
Yeah.
Adding
Exactly. So, yeah.
So if you get a pair where the manifold is already of general type, does it work?
Of course, yes. Because, I mean, this jet differential acts on any interior curve, so in particular on orbifold interior curve. So this is not, this is not interesting, right? Yeah. Sorry. Yes. Yes. So what you really want, the interesting situation is a variety where you do not have a jet differential, but it becomes of general type, and you opt to get some interesting, like in the log setting, right? If you take one here, it becomes true that you get logarithmic jet differentials. Yeah. Because you see that in the log setting, this is infinite, and you don't see this phenomenon here. So it works. OK, so then the first thing that was due to Bogomolov is the algebraic version, which we may say that S is pseudo-algebraically hyperbolic. So what does it mean? It means that there exists an exceptional set such that if you pick any ample line bundle, then there exists a positive constant such that, so this is algebraic hyperbolicity is a notion introduced by Jean-Pierre de Mailly, and you can formulate it in the pseudo setting where you have some exceptional loci. This is just what we do here, and this is how you can formulate Bogomolov original theorem. Then, for any morphism from a smooth curve to your surface, which do not lie inside this exceptional loci, you have a height estimate. So the height estimate here is just degree of the pullback. Okay? So this is a way to formulate algebraic hyperbolicity. So in particular, you see that this is a boundedness statement, which is useful because in particular, you will get that the scheme parametrizing a non-constant morphism from C to S is finite and quasi-projective. Okay, this is, in fact, a very effective version of getting boundedness here. And you have the analytic property by McQuillan saying that there exists also exceptional loci such that entire curve have to lie inside Z. So this is the statement of Bogomolov-McQuillan. So now,
Sorry.
yeah.
So you said, I didn't pay attention, it's a function alpha or
Yeah, in fact, it's just a product. It's a dot, if you prefer. It's linear in the genus, yeah. Exactly. So it was not, I think, originally formulated like that by Campana and Pound, but I think their proof is really an orbifold version of this Bogomolov-McQuillan statement. And, okay, I will also already quote the other classical theorem that I would like to generalize, is the famous Bloch-Cauchy theorem. Because somehow they have the same key character in both statements. This is the cotangent bundle, right? So this is the theorem Bloch-Cauchy. Which tells you the following. So you take X complex projective, and you suppose that the irregularity of X is strictly bigger than the dimension of X. Then we can, in this language, we can formulate that X is not Brody special. So this means that, recall you that this means that any entire curve is algebraically degenerate, right? So as I say, so my goal now is to explain you that we can somehow generalize both of these statements to pairs and get interesting results. So as I said, in both statements, but there will be some surprise. So in both statements, the key object is omega 1, right? Because in Bogomolov, you see that you have this numerical property, which is just here, in fact, to ensure that omega 1 is big. So you can reformulate this statement saying take S with big omega 1, then you have what follows. And you see here that you ask also a property of positivity of omega 1, asking that you have a lot of section here. So the first thing to do is extend this subject to pairs, right? So you have to consider the orbifold cotangent bundle. So key tools will be differentials on pairs. So here, when I say pairs, I mean really orbifold pairs with the standard coefficient. Okay, so I think, so this appeared a lot in the literature recently, and I traced back a bit in the history. I think this was probably Miyaoka who first considered this object. So then it was extensively used by Campana and Pound and many others now. Yeah. So here I will be in a very simple situation. I will consider smooth pairs, right? So X will be smooth, and it will be SNC divisor di with standard coefficient, right?
So that will be T as what?
So this, the support of delta will be SNC divisor, right? Just normal crossing. Yeah. So with Stefan, we've considered, of course, a much more general setting where everything is singular, and you can work with a singular sheaf of differential and singular spaces. But here, to stay simple, I will avoid all this and consider, so this is what we call in paper C pair. And so the idea is that you would like to consider differential forms on X with logarithmic poles, but of fractional pole order. This is the idea. Somehow, you would like to give a meaning to this object. But of course, due to this rational number, it does not make sense on X, right? So what you do is that you work on adapted cover. So this we have, we can use this. This was used also a lot in the birational geometry, the Kawamata cover adapted to these pairs. So this object will make sense on adapted cover. So this is just, you ask that this Q divisor become integral. So you pass from a rational coefficient to integral coefficient. So again, I will assume here, for simplicity, that everything is smooth. So that you can define quite easily this sheaf. So the price to pay to work with this object is that they will not live on X, but on X hat. So this, of course, puts some technical difficulties when you work with that.
So if gamma has some extra ramification,
of course, this is very important. So this is what somehow gives the whole difficulty. So you, I mean, also these statements are not trivial for uniformizable pair because you cannot lift interior curves. But it's even more difficult when this adapted cover, so I just asked this property. Of course, as I said, really have, in general, to have a global cover, you need extra ramification. You have to take this. So now you can define this sheaf of adapted differentials, which depends on gamma and lives on X hat through a residue sequence, exact sequence, right? So you just pull back the usual residue map. And you just say that this will be the kernel of the residue map, of the pullback of the residue map. Okay? And so you see that if you look in local coordinates, these formally exactly correspond to pullback of these forms locally, but this definition tells you that globally it makes sense on X hat. And so now, although, as I said, it was not formulated like that by Mihai and Frederick, I think we can formulate the statement now, because at that time they didn't use this sheaf. You used somehow, they had some technical difficulties because they wanted to work with symmetric differentials but downstairs. And this amount, you see, if you can make your cover Galois and make invariant and descend them. But of course, these make a lot of complication. And they work with this sheaf downstairs. But there is now, using this, there is a very simple characterization, is that their statement is the following. Is that let X be a Bogomolov-Chinkel example with the same numerical condition here on this sheaf, right? Which I will denote like this. And if you look at their condition, it exactly means that. So this is nothing else than this. So of course, this is up to multiplication by the degree of the cover. This doesn't influence this inequality, of course. And this turns out to be this. So I take again the notation of the Bogomolov-Chinkel example. So suppose you have this numerical equality, which in fact is nothing else than C1 square minus C2 for this sheaf. Then this variety is not Brody special. Another proof, at least the idea of the proof is very simple. This inequality tells you that you will have a lot of symmetric differentials here, that you can make it invariant and descend, and they will act on the entire curve. And you get some degeneracy through like kind of classical arguments. But now I want to state some of the variation we have of this result, getting towards an arithmetic statement. This was our motivation with Ariane. Can we prove some arithmetic statement? So yeah, said it quickly. So this inequality is about the Chern classes of this sheaf, in fact. So this is nothing else up to a fact, multiplication by a constant. This is exactly the square of the first Chern class of this sheaf. And now you can do the same as in classical Bogomolov. This will tell you that you will have many sections of symmetric powers of this. Right? But these, by definition, are made to act holomorphically on orbifold curves. Right? So even though you do not have symmetric differentials, a lot of symmetric differential on B, you have a lot of orbifold symmetric differentials acting on orbifold intercurves, so that you can prove this degeneracy statement downstairs. Right? Okay, so what is the theorem we have with Bartsch and Javanpeykar? Theorem with Bartsch, Javanpeykar. Is the following. So we need the same hypothesis as Campana and Pound plus an extra one, but which can be achieved. Let X be T such that we have this. Plus, we want that the elliptic fibration on B is not isotrivial. Which can be achieved in Bogomolov-Chinka. And we want everything to be defined over a number field. And now we take a variety, V, defined over the same, call it K, V, a variety defined over K. Then, the set of non-constant rational maps from V to X is not dense in X defined over the function field of V. So if you prefer, geometrically, it means that the union of the graph of all of these maps is not dense as rational points over the function field. So you could see that as a weak version. So this is what Ariane called transcendental rational points, because rational points would correspond to constant maps, right? So here we are looking at non-constant maps. So V has to be of positive dimension, and we'll look at this map. So I will just explain. So yeah, I'm very few time would like to speak about the. I will just explain you, not going into detail, what is it's an arithmetic statement. So at some point you need some arithmetic finiteness, and of course we don't have much at our disposal except faultings, right? So the point is to look at, so idea is of course we consider as the strategy is the same. You send everything to the orbifold base. And now you look at non-constant. So using a generalization of Bogomolov in the orbifold setting, you can get boundedness of this. So this will be quasi-projective. And now you want to study positive dimensional component of this, right? So you consider, and what you want to show, claim, is that in fact H has to be of dimension 1 and has to be Bartsch-Javanpeykar to a curve of genus greater than 2. Dimension of H is 1, and H. So if you prove this, it's finished, because you can use faultings. This corresponds to points of this scheme, right, defined over this number field. So the hard part is really to prove this claim, of course. And this uses many generalization of classical things in the orbifold setting. So we use the fact that, first of all, if you look at evaluation map of orbifold morphism, the evaluation map will be orbifold itself. And now you use a generalization of Kobayashi-Ochai, which tells you that you will have only finitely many dominant map onto an orbifold of general type. And then, thanks to this, you know that you will have a family of positive dimensional morphism from C to the surface, which is sending a point C to a fixed point X. And you can apply bend and break. But now you use that B of rule. So this will tells you that the dimension has to be 1. And then to get this, this is where we use the hypothesis that the elliptic fibration is non-isotrivial. So that B cannot be dominated of a product. Of course, H cannot be rational, but it cannot also be an elliptic curve because of the non-isotriviality of B. So this is the idea of the proof. So now I want to finish with the Bloch-Ochiai theorem. I'm using it to apply faultings here at the end. To conclude. No. Here, I've proved that component of this space. So I want to prove that this space is finite, right? There are only finitely many number of these maps. So this amounts to show that the k points of H are finite. So I prove that H is in fact a curve of genus at least 2. So by faultings, it has only finitely many k points. And this is why you get non-density. Okay? So now, the work with Stefan Kebekus is about generalization of Bloch-Ochiai. So as I said, you need so you send everything to an orbifold base and you need statement there. So the idea is, the problem I was interested in is, so it said X delta smooth, take an adapted cover, and so now, okay, you have a perfectly notion of adapted irregularity. So you consider adapted irregularity, which is just the dimension of the space. And now, the problem is the Bloch-Ochiai theorem is the following. Suppose that you have an adapted cover such that this space has dimensions strictly bigger than X. Then, is it true that X delta is not Brody special? Right? This is the exact analog for pairs. Of course, so now you always strive to generalize the classical proofs. So this is known, of course, when delta is 0 and in the log setting, this Bloch-Ochiai. And all proofs goes through the Albanese or the quasi-Albanese. So immediately comes the issue, is there an Albanese adapted to this? What is the Albanese? So all proofs, all classical proofs, use Albanese. So the first step of the game is construction of an adapted Albanese. So this is, there is kind of a natural construction to consider. This kind of construction was used in a kind of dual way by Zuo. Zuo considered Albanese adapted to a subsheaf, to a subvector space of global one forms. So you can do the following. So you know what you would like for an Albanese of adapted differentials to be. So the idea is the following. So you have your cover, you have the Albanese of the cover, and then you will take a quotient. And this will be the Albanese. So the whole question is, what is this B? This B is kind of natural. What do you want? You want that pullback of one forms here go to adapted differentials. This is the least you have to ask for an Albanese map to be. So B And this immediately gives you the definition of B. B is the smallest abelian subvariety containing the image of the orthogonal of V, where V is the space of adapted one-forms, which you look, so I will take only finite multiplicity so that this really lives here. And pi is just the quotient defining the Albanese. Right? This is the natural notion to consider, and such a map will have the property that if you take the pullback of one from here, it will do adapted differentials. Sorry. Yeah, sure. Thanks. It's upstairs. The main issue that puzzled us for some moment is, do we get back all forms? Okay? And the answer is no. It can happen that you do not get back all forms with this. So, in fact, there are very simple examples that Frédéric Touzé made us realize. In very simple example, even without boundary on curves. So the problem is that in this way, you do not get all adapted one-forms. It can happen. It can happen that you know the. And the example are kind of very easy. So you consider just ramified covering of curves without boundary. What is the adapted sheaf? Adapted sheaf is just the pullback, right? And now you can construct an example where you get indeed more section here. Than downstairs, but you will not be able to get these forms here with this construction if you add the property that the prime variety is simple. So the prime variety is just the kernel of the induced map between Jacobians. And if this is simple, it means that in fact, what you have constructed here, you will always get back to the Jacobian of the first curve, in fact. So you will never achieve to get back these adapted forms that you get here. So this, I think I am kind of almost finished. So this made us, define another notion of irregularity, which is the dimension of this adapted Albanese. And then with this new definition of irregularity, we can prove Bloch-Ochai. The proof uses Nevanlina theory for branch covers in abelian variety, which is at our disposal. But the general problem stays open for this condition of irregularity. And at the moment, we cannot achieve because of this phenomenon that there is no yet, I don't know if it exists, another construction of an adapted Albanese which enables you to get back all adapted differentials. Okay.